Hello. Let's start. My name is Piotr Zwiernik, and it's my great pleasure to introduce Jonas Peters. Jonas is he's a professor of statistics at the University of Copenhagen. His background is in mathematics, partially in physics, and in statistics. He is an extremely successful teacher and science popularizer. His recent book on causal inference has become immediately a very important reference in the field. This book, written jointly with Dominik Jancik and Bernard Schölkopf, has also recently received the Causality in Statistical Education Award from the American Statistical Association. Jonas is also a very active contributor to the community of statistics and machine learning. He's an associate editor in two major, the most important journals in statistics, namely the Annals of Statistics and the Journal of American Statistical Association. He's also the chair of the forthcoming Uncertainty in Artificial Intelligence conference, which is one of the major conference series in machine learning. His brilliance and courage have been recently rewarded with the Guy Medal in Bronze from the Royal Statistical Society, which is one of the major awards in the field of statistics. I said courage, and most of the mathematicians would always think, why do you need courage to do research? So let me give you a little bit of the context. The field of causal inference is actually pretty competitive. There are a lot of big egos in this field. People have very strong opinions about how to do certain things, how not to do them. There are different fields in which these ideas have been developed independently, like biology or economics. And for that reasons, research seminars in causal inference can get quite brutal, actually. And I have witnessed personally Jonas giving one of such seminars in my department, in the Department of Economics in Barcelona. And I was truly amazed with how he was handling the audience. It was an amazing experience. Finally, he's an extremely open and friendly person, and invite him to your department for a couple of days, and when he leaves, he will probably know your colleagues and your department better than you do. So join me welcoming Jonas.
Can you hear me okay? Does this sound fine? So thanks a lot, Piotr, for the, I think, two kind words. Thanks also for the organizers for the invitation. It's a great honor to speak in front of such an audience. So far, the conference has been wonderful for me. I learned a lot of things, which might be partially due to the fact that I know almost nothing about algebraic geometry. So I really enjoyed this. And my plan for today is to talk a bit about data science and causality and introduce you to some of the problems we are dealing with. And I'm trying to highlight some of the possible connections to algebra. And I'm just warning you, it might be that these connections are trivial or impossible to solve. So this is very hard for me to judge. I should say that I'm sort of talking about a couple of works. The three main parts are due to these wonderful collaborators, but of course I'm mentioning more results than this, and there should be more names up here. I apologize for incompleteness. Okay. So in data science, I would say that we are seeing many success stories. So deep neural networks are applied everywhere, and personally, I think some of these applications are very impressive. So if you look at computer vision on the top right, or also machine translation, I think these systems tend to work very well. However, there's also something that goes beyond this. And why is this? These applications that we are seeing, many of them focus on prediction. What does this mean? You have huge data sets, let's say 1 million images that are labeled. Each image has a label, there's a cat in it or not. And then you're trying to sort of learn the patterns and then apply it on a new test data set. And I would argue that there are many problems that go beyond this predictive tasks. So there are many examples possible. I just show a few here. So what you see is a map of Colombia, and actually, hopefully it's visible, the forest loss. These are the light areas. And people are not only interested in predicting forest loss, but they really, of course, want to understand, well, what is it that makes forest loss occur? Why? Because we want to change it. We want to introduce policies that actually reduce the forest loss at some point. And this is a question that goes beyond prediction. So the red points you see here, this is actually a project that we are currently involved in with the colleagues from Berlin. These are violent conflicts. So they are interested in the question, what is the causal relationship between violent conflicts and forest loss? In biology, you have many similar questions. So here you see an example from yeast data. This is the activity of 2 genes. And again, I would argue we're not only interested in predicting, but we would like to know what happens if we delete, let's say, 1 gene. Is it that we see a change in activity of a target gene or not? Again, this is an interventional question, if you like. Now, there's also another sort of area of problems that I would loosely describe with distributional shifts. And so what is the idea? In many situations, you have that the test data actually differs significantly from the training data. And then, of course, you have to be careful, because if you're training on something and then you see something else in test, you may fail. So you can think about autonomous driving, and suddenly you face a situation you haven't seen before. So what is the car going to do? You can also think about problems of reinforcement learning. So this is a very old computer game where you sort of try to learn the rules of this game, and then at some point these machines are very good in solving the game, but then they are faced with the next level. And what is it that we can transfer? So do we have to start over again and learn everything from scratch? Or personally, I would like to add one last example here. I remember very well when I was living in Switzerland, I tried very hard to learn the local accent from Bern, and at some point I thought that I understand it, but then a friend of mine actually introduced me to a video with this title. I highly recommend watching it. This is a story from Franz Hohler, and I miserably failed. What was the problem? It turned out this is actually not real Swiss Berndeutsch, but this is like a sort of half Berndeutsch language and half made-up language. So again, the distribution between training and testing is very different, and the question is, well, how can you transfer something? So these 2 problems on the left are clearly causal. The ones on the right maybe less, and if time allows, I come back to this later. So what is a causal model? So this is the first thing that I would like to introduce you to, and maybe one comment in data science, we are very well used to the fact that we have a data generating process and we would like to model this. So you can say, well, you're measuring 5 random variables, and your model is you have a 5-dimensional Gaussian distribution with a certain covariance matrix, and maybe you're trying to learn the parameters from the data. Now, a causal model is something else. It has to do something more. It does not only have to model the distribution that you see, but it also has to model the distributions that come out after an intervention. So you also, as a causal model, you also need to provide sort of distributions that we call interventional distributions that say what happens if I intervene on some of these variables. You can think of policy changes. And this is a picture that I like. So you can think about a causal model, and I will introduce you to an example, a structural causal model. There are other examples as well. You can think of this as being a device that gives rise to a distribution, but also at the same time of interventional distribution, what you can see here on the bottom. And then also often some of these causal models output a causal graph. This is very nice for illustration. We'll see this in an example. And then some of the causal models output counterfactuals. This is something that I'm not going to talk about today. So now I would like to cite Alicia from this morning. So here are now the vegetables. So what is a structural causal model? So I'm going to explain this to you. I'm going to try to explain this to you at an example. So let's say we are interested in modeling the relation between altitude x and temperature y. So what is a structural causal model? It's something very simple. So it just contains two assignments, namely one for x and one for y. And you can think here of computer code if you just write lines of computer code. So here x is just a noise variable whose distribution is specified. Let's say it's a Gaussian 0, 1. So you can already guess this is maybe a better model for Denmark than for Switzerland because the mean is 0 here. And then y is minus 6 times x plus some noise. And where does this come from? Well, if you measure the altitude in 1,000 meters, then you have this decline of minus 0.6 degrees every 100 meters. So this is a model. So the first question, and I would argue it's a causal model. So the first question is, what is the distribution that is induced by this model? So I give you 10 seconds to look at this. So now I claim there's an induced distribution over x and y. Well, x certainly is Gaussian, right? Y is Gaussian, so here, in fact, in this case, they are jointly Gaussian, and what are the means? Well, there's a 0 for x and y. What is the variance of x? This is just 1. What is the variance of y? Well, we have 36 plus 1, so it's 37, and the covariance is minus 6. So what do we get? If I didn't make a mistake, so we get the joint Gaussian distribution. Is this a particularly good model? I'm not talking about this. So of course, having a Gaussian distribution in this example is a bit of a questionable thing to do. The main point is it's a model, right? And we will see how to validate these. But this is the first part, but now we need to see, can we also induce interventional distributions? And we can, and this is really in the simplest way you can imagine. So imagine that you're trying to model a certain country and you have different measurement stations, and now you're intervening on the altitude, which means that you maybe take helicopters and each of the measurement stations is lifted up. So how do we model this mathematically? We just replace the first equation or assignment and set it to x always being 3. So they are all now in 3,000 meter altitude. What happens now, this is again like inducing, of course, a distribution, and now this is what we call an interventional distribution. And what you, of course, see is that the distribution of y now differs. So this is a different distribution of what we saw before. Now x is, of course, discrete, and y is now a Gaussian distribution, but now the mean changed. Because, of course, you intervene on the altitude, so it will get colder. So this is what the model predicts. What else can you do? You can, of course, also intervene on the temperature. How would this look like in this story example? Well, maybe you go to like all these measurement stations, put a heater there, and say, we now heat this place to a random distribution, let's say with mean 42 degrees, and then a variance of 3. So this would also be an intervention, and now you can already guess what happens to the altitude of these places. Well, according to this model here, nothing. So they stay on the ground, so that the marginal distribution of x is still the same. It's still a Gaussian 0, 1 distribution. But again, this is a distribution, what you see here, that differs from the observational distribution. And a side comment here, the graph, you realize this changes now. Why? Because now y doesn't depend on x anymore. So the edge disappeared. So that's about it. So this is really the most important thing you have to know about causal models. So of course, this generalizes now to more than 2 variables. So in general, what is a structural causal model? We just have, if you have 4 random variables, we have then 4 assignments, and they all look like this. So you always have variables on the right-hand side. How do you draw an edge? Well, how do you construct the graph? Sorry, you always draw an edge from the variables appearing on the right-hand side to the variable appearing on the left-hand side. So here you have an edge from x3 to x1, for example. Now, for today, we will assume that the noise variables are jointly independent and that the corresponding graph doesn't have any cycles. Of course, you're asking, well, is this necessary? And it's not. You can relax these assumptions. If you're interested, please join the field of causality. But for today, we are going to make these simplifying assumptions. This structural causal model, again, also induces in what we call observational distribution. Why is it? So again, get 10 seconds to think about this, about a possible proof. So why do we have that these structural causal models always induce a distribution over the variables x1 to x4? So one possibility to see this is, again, think about computer code on the left-hand side. So if you would like to sample from this distribution, what you would do is you would start with a random variable that doesn't have any input, and in this case, x3. So you sample from the noise distribution, you plug this in, and then you have one observation for x3. And then you can recursively go to the next variable. So here, for example, this allows you have a value for x3. This allows you to plug this into this equation and then get a value for x1. So this is what you would do in practice, and this is actually also close to how the proof works. As before, we can intervene. So you can intervene and set, for example, x1 to 0, so independently now of the value of x3. And this is an intervention distribution, and this is where the notation comes from. So here we call this p, and then we do a subscript do x1 to 0. This is a famous do notation from Judea Pearl, and it indicates that this distribution arises after we have intervened on x1 and set it to a constant 0. And again, here the edge disappears. You can look at other intervention distributions as well. Of course, you can also intervene on x4. So this is hopefully not so complicated. This is one causal model. What do we need? We need really to have these assignments, and if we are given them, then we can sort of look at the distribution that are induced by this. I should say also, maybe with respect to the talk this morning, so I'm not talking about this today, but if you're interested in dynamical systems, this works exactly the same way. So then here we are looking at IID data, but if you're interested in chemical reaction networks, for example, think of this as being your derivative. And then the right-hand side, this is what occurs, for example, if you look at mass action kinetics. These are all the differential equations. And then the interventions are also natural, right? So you can intervene in the system, change, for example, some reactions or reaction rates, and this will correspond to a change of one of these, or possibly more of these differential equations. So it works exactly the same way. The important part, I stress this, hopefully it helps. So the important part is really the modularity of this structure. So you're intervening on one variable, and then the other variables, the other assignments, they don't get changed immediately. This is like one definition that could be helpful for gaining intuition. I'm not going to use it throughout the talk, but you can now think about models being equivalent. So if you have a causal model, you can either view this as a probabilistic model, so you can say that two models are probabilistically equivalent if they entail the same observational distributions, or you can view it like as a stronger model. You can say two models are interventionally equivalent if they entail the same observational and interventional distributions. So personally, I think this is helpful to think about it this way, because it also makes you think about how to evaluate or falsify such models. So if I'm claiming I have a causal model, and this is the causal model, how could you falsify my model? How could you prove that I'm wrong? Well, you could look at the observational data, but you can also look at interventional data. And this is what happens all the time, for example, with pharmaceutical companies. They propose causal models all the time. They say, if you take this drug, you get better. So how do we check whether these pharmaceutical companies are right? We do randomized control studies. And this you can see, it's a bit simplifying now, but this you can see as an interventional experiment, where you set sort of the variable indicating treatment. You just randomly set it to the outcome of a dye, for example. And then if this corresponds to what the pharmaceutical company said, then you're saying, okay, I have no reason to falsify your model. I've learned that it's always important to put visual breaks into the talk. This is also what I have done today. So what have we talked about? So far, I only sort of defined what a causal model is, and we are going to do, of course, a bit more, hopefully fun stuff after this. But I was wondering whether there are any questions, because I would rather like to drop a couple of slides at the end compared to not being clear enough in what I'm saying. Okay, so you have another visual break, there you have another chance. So what is happening in practice? Well, you can already guess it. In practice, of course, no one is giving you the causal model. No one is giving you the structural causal model. So the question is, can we infer it from data? And this is known under the name of causal discovery. So think about that we are receiving data from a system. You can think about IID data, but this can be more complex as well. It can be temporal, or it can be spatial as well. And we are trying to find the underlying causal model. Now, the causal model, I said, is sort of a structural causal model. So you can also think about, well, is it possible to estimate the underlying graph? And what my plan is for today, to talk about 3 ideas of how this could be done. And I'm sort of skipping a lot of the theory. I just would like to sort of present the ideas to you. What is the first idea? The first idea is to use conditional independence. So how does this come into play? So you can actually prove that whenever you have a distribution that is induced by a structural causal model, then the Markov property holds. So what does it mean? So assume that we have a distribution that is entailed by a structural causal model over some variables x with a certain graph. And then we have for all disjoint sets that whenever they are d-separated, so whenever x and y are d-separated by z in a graph, this implies conditional independence. What is d-separation? It doesn't matter. So this is something that you learn in graph theory, but this important thing is this is a criterion that only depends on the graph. So there's nothing else that you have to consider. You only have to look at the graph, and then you can read off, is x and y d-separated by z? Now, according to this proposition, this implies that we have a conditional independence. And what is nice now, well, this is a property in the distribution. So if we are given data from the underlying distribution, we can, in principle, test this thing and then infer something about the graph structure. This is, of course, well known. And how can we exploit this? So this is a historical paper from 1950 where people already thought about the connection between lung cancer and smoking. And this is actually, from my point of view, surprisingly well-written paper that analyzes this. I'm not showing you all the data. This is a table that I like. So here you have patients with lung cancer and not lung cancer. And I just want to highlight the fact that there were some people who smoked a lot of cigarettes in their lifetime. So what is it? The politicians said, well, we see this dependence, so probably smoking is causing lung cancer, so we should introduce something like a tobacco tax. The tobacco industry didn't find this too appealing. They said, no. So there's a dependence, but this is actually, it could be due to some common cause. So for example, it could be that only old people smoke and old people develop cancer as well. So how can we distinguish between these 2 models? This we can use using conditional independence, because if this holds, if this model is true, then we should find a conditional independence in the data. We should be able to find that smoking is independent of cancer given age. Why? Because the corresponding d-separation holds in this graph. So this is, of course, there are many more, much more sophisticated methods, and a lot of people in the room have also contributed here. But this is sort of the essence of the idea, connecting the graph to conditional independencies. So this is why I would briefly like to talk about this conditional independence here and how to actually test it. So what is conditional independence? This is a reminder. If you have 3 random variables with a certain density, then we have that the conditional independence holds if we have that the conditional density factorizes. So P of xy given z is the same as P of x given z times P of y given z. Now, this is the same thing as, and I like this a bit better, P of y given xz is the same as P of y given z. Why do I like this better? Because I think it's more intuitive. It means that if you know the value of z, then x doesn't carry any information about y anymore. So if you know z, then you can remove x here because it doesn't help you to predict y. So this is the definition of conditional independence. Now I'm doing something risky. I'm talking about the algebra side of the story. So we have heard about this already yesterday in the talk. And here's one way of looking at this. So if you have discrete random variables, so just shout in when I'm saying something that is stupid. So we have 3 discrete variables that take only a finite amount of states. Now, what is the probability? Well, we have to specify this probability of x equals 1 and y equals 2, for example. And we just call this now P12. So this will be one of our variables. So then, if you want to talk about the whole distribution, because we have finitely many values, this just corresponds to this matrix. And we have seen this in the talk yesterday. So now we have that we have a independence between x and y if and only if this matrix here is of rank 1. So you can look at the 2 by 2 subdeterminants, and this is the motivation for defining this independence idea. This is, of course, well known. This is not what I did. I have some references there. So what is the independence ideal? So you're looking at the 2 by 2 subdeterminants, and they should all vanish. So you're looking at this ideal generated by these polynomials. You can do the same thing for conditional independence. The only thing that differs is that you now have to include the value of z here. And note that this is, of course, always the same value z that appears in these 4 terms. Why is this useful? So you can actually now do some, which I found very nice algebra. So you can look and analyze intersection property. This is a property that is well known. It's just a question, well, if x independent of y given z and x independent of z given y, do we have that x is independent of y given z? It was very well known that this is true for positive densities, for example, but as far as I know, the question of characterizing when it holds was open and was posed as an open problem by Dürton, Sturmfeld, and Sullivan, and then Alex Fink solved this in 2011. And how, just looking at algebraic properties, so if I remember correctly, this was a primary decomposition here. Now the question is, so if you think about this smoking problem, if you're really honest, then h is actually not a discrete random variable. It's continuous. And the question is, what happens if you go to continuous random variables? And this I would like to at least briefly talk about. Why? Because there's something that happens in statistics that is interesting, I think. So as far as I understand, the Gaussian case can be dealt with as well. But the continuous non-Gaussian case, I'm not aware of any approach on the algebraic side. Why do I think this is interesting? Because in statistics, there's something interesting happening when you go from discrete variables to continuous random variables. And this is what I would briefly like to talk about. So what is it? This is actually a problem that has been looked at for some while, sorry. David found that there are practical difficulties if you increase the dimensionality of Z. Linton and Gonzalo thought that there does not appear to be any fully non-parametric test for condition independence. Bergsma hypothesized that condition independence is much harder to test than independence. Gretton and Shirkov argued that for finitely many data, condition independence testing may actually be arbitrarily hard, and then you also saw some empirical evidence. These are sort of intuitions. There was no proof, and even though this is sort of a lineup, I think the results may come a bit as a shock. And why? Because there's a reason for all these findings. It turns out that there's no non-trivial conditional independence test if we go to continuous random variables. So what is this result saying? I just presented to you on the next slide, so try to make it formal. Let's consider distributions where this holds. So now we are looking at distributions that have a continuous density, and we look at the subclass such that we have this conditional independence, x independent of y given z. We look at a certain sample size. This is the data that we receive. And now what is a test? A test is just a function that takes the data and outputs 0 or 1. And if it's 0, the test thinks that indeed we have conditional independence, and if it's 1, it thinks that we have conditional dependence. And now we say that this test has a certain level if, now this is not as complicated as it looks, if for any distribution for which this holds, the probability of rejecting, so this is the probability of making a mistake, is actually less than alpha. So think about 5%. So this is what we call a statistical test. And this should hold for all distributions under the null, so you can put the supremum here. And now what is the statement? The statement is that actually these tests don't exist. So in which sense? Given any sample size and any levels, think about 5%, and any potential randomized test that has the correct level, then you can actually show that you don't have power against anything. So for all alternative distributions, so for all distributions for which we have conditional dependence, you have a very small probability of rejecting. So this means you basically, the only thing you can do is you can say, I always accept the null, and of course this is a very useless test, but this is the best you can hope for here. And this raises a couple of questions that fortunately I do not have to answer, but I think I would like to discuss them. The first thing is to note this is very different from unconditional independence testing. This is important to keep in mind. And now what are the questions? The first one is, what does it actually mean for this first idea? So what does it mean that if you want to exploit conditional independencies, but as soon as we go to continuous random variables, we cannot test this anymore? And of course, this also raises the question, well, what happens actually, what does it mean for graphical models? These are models that encode exactly these conditional independencies. And then the last question I was just curious is, what happens on the algebraic side? And maybe I can say one more word about this. So it turns out that not all of these properties break down if you go from discrete variables to continuous random variables. For example, the intersection property that I showed, this is a bit of a coincidence result because it's not hard to show. I was able to prove this with basic tools for continuous random variables as well, and some people in the audience pointed me to the literature here. So this is basically the same result that carries over from discrete to continuous random variables. However, in this conditional independence testing, something weird happens, and I was wondering whether there's an algebraic side to the story. This is my next visual break. So what have you seen? This is an idea where we are relating the properties of the graph, these aberrations, to properties in the distribution, and we are trying to exploit them. Maybe to round off the story with the tobacco industry, so you can be wondering what they actually tried to do, and maybe some of you know these stories. I think it's quite interesting. There were some statisticians becoming really rich there. So you could actually now you could say maybe they said, well, it's a continuous dependence and you cannot measure this anyhow, but of course they didn't know about this result. They did something else. So they said there's indeed a confounder, but it's genotype. And why is this so brilliant? Because if you would like to test this, we are seeing you should do a conditional independence test. But this is so brilliant because this was in the 50s and there was no way of measuring genotype. So you can actually not falsify this model. So this is why some statisticians became very rich by coming up with this idea. A lot of people died. Are there any other questions? Or are there any questions regarding this first idea?
What if you just put the ages into bins like you do?
Yes, so what happens if you, the question is, what happens if you put the ages into bins? And this still works. It's really, so because then you basically have the discrete random variable. And if it's true that the dependencies can be expressed in this way, but this is a simplicity assumption, but if this holds, you can still do conditional independence testing. So if you place simplicity assumptions on the conditional, you can still perform the tests. But if you are really honest and say, I have a continuous random variable and I don't want to specify the dependence, then you cannot do it anymore. Yeah, but of course, it's a good and important point. Yeah?
So can you say the distribution assumptions again?
So what are the distribution assumptions? It's just to have a continuous density. Yeah, it applies to Gaussian. And why is this? Well, because so what happens, right? You can test for vanishing partial correlation, but this is actually neither sufficient nor necessary for conditional independence. So this is why vanishing partial correlation is not a counterexample. Okay, 2 ideas to go. So again, we are trying to find ways of making sense of causal relationships by looking at data, and I would like to show you this plot here. So what do you see? Over the years, we collected a couple of real-world data sets. These are always pairs of random variables, x and y. There are a few more now, and these pairs, we always know the ground truth. So think about something like availability of clean drinking water and child mortality rate. So now I would like you to focus on this particular plot here. This is one data set, and I'm not telling you what it is, but I would like to make a vote, or I would like you to make a vote, and you can now vote for either that x is the cause or that y is the cause. So y is on this axis, x is on this axis. So I'm not telling you what it is. Of course, you cannot use conditional independencies because there are only 2 random variables. So I would like to make a poll here. And of course, you have to decide. So who believes that this random variable x is the cause in this example? Who believes that it's this random variable? And the rest doesn't care yet, but you should. So this experiment never fails. So indeed, it's this random variable. And what is it? It's day of the year and temperature. So indeed, you have a causal relationship there. And where does it come from? It's somehow, what is the intuition here? If you want to explain y from x, this you can do with a very simple model. Whereas if you want to explain x from y, you somehow need to have a complicated model. And this is an asymmetry that you can formalize. And this is the second idea, so different ways. But this idea says you can restrict the class of structural causal models to obtain identifiability. OK, how does this work? So imagine that you have a distribution that is entailed by a model like this. So now this is a structural causal model with a special form because we have a plus sign here. So y is a function of x plus some noise. Then the statement is that you cannot find a backward model. So there's no backward model. There's no function g such that x is a function of y plus some independent noise. And why is this? So we're going to prove this by an example. So you look at a specific function, namely x cubed, and I just plug in some of the distributions, and now I show you the scatter plot. So this is y as a function of x. Here you see x cubed. Now we know the distribution of x, so we can sample the points. So this is how it looks like. So why is it that we cannot find a model from y to x? And in order to see this, you can tilt your head a bit, because what we have to do is we have to regress now x on y. So we are looking for this asymmetry. And where does it come from? Well, if you're trying to regress x on y, I did this for you. So this is the function that you will find. So this is the regression function. And now what you see is that if you look at the residuals, then the variance actually changes a lot over the y's. So here you have a very large variance, whereas here you have a very small variance. And this is the intuition. So this is not a valid backward model because the variance changes, so the residuals are not independent of the input anymore. It's, of course, a very strong model assumption, but it's just saying, well, if you're willing to make such an assumption, you can, again, infer structure from data. This generalizes, so you can ask, well, if you have more than 2 variables, if you have a set of random variables, this still holds. So you can ask, if you have a structural causal model, can I identify the graph from the distribution? And in general, the answer is no. But if I'm willing to make this additional assumption of simple functions here, like assuming additive noise, then you can indeed identify the structure if and only if the functions are nonlinear. So it's a bit of a, I think, interesting result that the linear Gaussian case that we know and love, this is really the hardest case here. So as soon as you have nonlinear functions, or in fact non-Gaussian noise, you can identify the structure. So where does sort of an algebraic question come into play? So this is, again, only an idea. Let's see whether it works. So now the question is, well, what happens if you have data, right? So this is a theoretical result, but if we are given data, how can we find the graph that actually shows us the causal structure? And maybe this helps to think about it. So imagine we only have 2 variables again. And here in the red subspace, you are collecting all the distributions that are induced by structural causal models from x to y. And here in the green one, you have distributions that are induced by models from y to x in this additive noise model case. And then the intersection, we know these are only the linear Gaussian cases. So this is the intersection. Now, if the true distribution lies somewhere here, what can we do? Well, in reality, we are given a data set. So we are given an empirical distribution, p hat n. And which one do you go for? Do you think this comes from the red or the green model? Well, one way of solving this is just to say you choose the subspace that is closer, for example, in Kullbaum-Leitner divergence. So here for each graph, we now compute the distance, and then we choose the closest subspace. This is what you can do. It actually turns out to be simple in this case. So what do we have to do? We have to compute this distance. So if we are given an additive noise model, over these variables and a certain sample size, we can compute the distance, and this is the blue stuff. So for a certain graph, this is the distance to the subspace. So how do you read this? So first you regress all the variables on its parents, then you look at the residuals, and you look at the logarithm of the empirical variance. And this intuitively makes sense, of course, because if it's a good fit, we expect these variances to be small, and this means that the distance is small. And then what do? Well, you just look for the graph that minimizes the distance, and this is also known as maximum likelihood, of course. It's the same thing. You can do this in the example from above. So here you can just see the scores, and of course it's not surprising that this model fits much better. So indeed the score is much lower than this weird backward model here. And this is in well correspondence to most of your intuitions. Now, what is very easy to see that this is you can yield consistency, consistent estimators, but what is a bit harder, at least for me, is to answer the question how much nonlinearity is actually needed for a given n, because if you are close to the section, so I think I have the picture again, so if you are close at the intersection, then of course you need a lot of large sample size, because these subspaces will be very close. And this picture that I drew is of course a toy picture. I have no idea how the geometry here looks like. But I think this is an interesting question to look at. Why? Because, so you can answer, well, how much nonlinearity do I need for a certain sample size? But you can also use these results for computing confidence intervals. So what do we have? We have a very simple first step that is far from being satisfying. So we have a distribution that is, if it's entailed by a structural causal model like this, so we have a measure for nonlinearity here, this is the beta, then we know that the distance to the wrong subspace is positive. This is what the theory tells us. And in this case, the simple case, you can also compute the distance. But of course, this is a very restricted model class. And the question that we have, and this was too difficult for us, is whether this can be computed in general cases. So this is really only a first step, and the question is, or my question is, can algebraic geometry help here? And there's some work that I would like to stress, because I think it's very interesting work from Robin Evans in Oxford, model selection and local geometry, where he looks at semi-algebraic sets for models and then computes these, looks at these intersections. You can imagine that if you have two models where the tangent space is the same, then it's actually much harder to distinguish these two model classes from data. And you see there's a very nice relation to parametric rates. So this could be one step how to approach it. Okay, this I think my last visual break. What you see here is, to the best of my knowledge, is the only ever recorded albatross in disc golf on YouTube. Are there any questions? Yeah?
The 12 and 13 didn't look that far apart that you had.
Yes, so the 12 and 13 don't look far apart. So in fact, so here the difference, I mean, if you look at the models, is huge, right? But of course, and in particular, so what you would like to, if you want to specify, is this significant or not? I think you need to answer this geometric question. And this is what we would like to do. Because in reality, of course, you can now say this is the easy way out, right? Well, this is just an indication, and then the biologist should do some further up experiments or something. But I think on the statistical, from the statistical side, we should be able to do a bit better. Okay, so then there's one last idea I would like to talk about today. This sort of the third idea, and this is an idea that tackles actually a simpler problem than the full causal discovery problem. So we are looking at a target variable y. So let's assume that we have one variable that we are particularly interested in, this y, and we are trying to find not the full causal model, but we are trying to find which of these predictors, x2, x3, x4, x5, are actually causal for y. So this is a much easier problem, and what comes for a rescue, so we assume that we are observing the system in sort of different states. So what do I mean by this? This is the idea of exploiting invariance. So assume that we have an underlying system that is completely unknown, but we receive sort of two different data sets. You can think about a blue data set and an orange data set. So there's some heterogeneity in the data that we are going to exploit. How does it work? So this is sort of what we are hoping for. This is the sort of code, and I'm trying to explain how this works. So the idea is now to use, of course, the data for X, the data for Y, and then in addition, you use this vector of indices that just indicates from which of these two data sets the data point comes. So is it a blue one or is it an orange -1? And then the hope is that you get out something complicated, but this is, of course, the important part here at the end. You get that indeed X1 and X3 are the causal parents in this example. So what do we do? This is an extremely simple method. And again, I think or I hope that it can be improved. So what is it based on? It's actually based on this modularity. So when you remember these structural causal models, it was actually the case that we have these different lines of codes. And if you replace one of these lines, then the remaining stuff remains the same. And this is the underlying idea. So imagine that we have the two different data sets, the blue one and the orange one, and they are actually generated by the same system, but the orange one has these interventions, so where you perturb some of these variables. Now, what this fundamental assumption, it's sometimes called modularity or autonomy, means is that, well, this conditional of y given x1 and x4, this doesn't change between blue and orange if you don't intervene on y. So because this is, if you can think about this line in your computer code, this didn't change, right? So this means that this conditional distribution of y given x1 and x4 is exactly the same in the blue and the orange data set. And again, we can formulate this as a conditional independence if you like. So if A is the index indicating the data set, then we have A is independent of y given x1 and x4. So this is this underlying principle. And now we're just exploiting this. Why? Well, in reality, we don't know the truth. We don't know whether this is the graph that we are looking for. So what do? Well, we just look for these invariant sets. So we define a subset of variables to be invariant if you have this conditional independence here. And then what do? We just test a lot of models. So here, if you test, for example, the model S equals 2, then you will find that this is actually not an invariant model. And why not? Because the conditional distribution of y given x2, this changes. So here it's actually a linear model, and you see that the regression coefficient in the orange data and the blue data, they are different. So here this is not an invariant model, and you can say, well, then it cannot be causal. So what do? We do the simplest thing you can imagine. You just run through all the possible models and always check invariance. So the idea is to use the blue and orange data and search for invariant models. So you make this long list of this long table, and you always check, do I have this invariance or not? And now the point is, there's a lot of structure in this table that we don't know how to exploit. So there's a lot of structure, and we are sort of doing the dumbest thing you can imagine. What we are doing is we are collecting all the yes answers and take the intersection. So this is what's written here. So you look at all the invariant sets, and you take the intersection, and in this case, it's indeed the true model 1 and 4, but in other cases, it might be smaller. So what is the idea? Well, one of these yes answers will be the true causal model. You don't know that it's the true causal model, but this is by assumption. This will get a yes answer with a large probability. So what we do is we make actually the set smaller, right? So one of these sets that we are taking the intersection over is the true model. We are taking an intersection over many things, so this becomes smaller. A lot of structure we are not exploiting here. But why do we do this? We can actually prove that you get a very nice guarantee for this output as hat. So in general, of course, this is the invariance that I showed you, but I've also told you that independence testing is hard. So what you can do in practice, you just make an easier model assumption. So basically, you're modeling this dependence here, and you can look at linear models if you like. And then you check for these linear models. And I just very briefly show you sort of the main results. So you can prove, because we are taking the intersection, it's very easy to see that with large probability, the output that you get is actually a subset of the true causal parents. This is not related to linear models or whatsoever. So you can do the same thing for survival data. You can do the same thing for nonlinear data. You can do the same thing for differential equations. So the idea is really that we have this modularity that we are exploiting. And the question here is, can we somehow instead exploit the structure of this invariance table? We are not aware of this, but there's a lot of structure that we are not using. Taking the intersection seems to be a bit of a dumb thing. Okay, so I skip a few slides to allow for discussions at the end and just conclude with one last idea. This is relating to this distributional shift that I mentioned at the beginning. So I said that if you just look at prediction, so this is what you can do in many situations. If you think about machine translation, I think this is the best thing you can do. You get models that are very good in prediction. Now, if you're interested in causality, then looking at these invariances is one of the ideas how to actually get a causal model. And now the last idea I would like to at least briefly mention today is whether we can exploit something in between. So can there be a benefit from trading off invariance and predictability? And the hope is that this helps in these situations where you have distributional shifts. And this is what you can show. So the idea is find a trade-off between this invariance and predictive power. So here's one idea how to do this. This is something that we looked at recently. So again, you have a target variable y. You have a couple of predictors, and you have your, what we call an anchor. This was the index indicating whether you're in the blue or the orange data set. And then the question is, can we trade off invariance and prediction? And this is only one way of doing this. This is, again, not an optimal way, but this is what we can look at. So here you find a term that measures predictability. And here you find a term that measures non-invariance. And now what you have is you have a regularization parameter gamma that is sort of the knob that you can turn from one side to the other. What do we do? Well, this is a term that we can optimize very quickly about. This is only one way of measuring non-invariance, but this is what we can deal with in practice very efficiently. And you see that this may remind you of a way of regularizing a model. So this looks a bit like a lasso model or a ridge regression, where you are now not regularizing with the size of B, but with a non-invariance. And you can actually show that sort of this. Why would you like to do this? Well, you can show that this is the optimal thing that you can do if you're interested in prediction, but not on the training data set, but on a test data set that is constructed by shift interventions. And the gamma controls what kind of shifts we can allow for. So the larger the gamma, the more shifts we can allow for. So this is maybe helpful for some of you. So again, if you set gamma to OLS, to infinity, then you receive ordinary squares, just focusing on prediction. If you let gamma go to infinity, you find a causal method. This is instrumental variables. And you can, of course, now exploit the stuff in between. I feel like I should skip the theorem here and maybe just talk about this interpretation. So if there's more than one invariant model, you can choose the best predictive model. This is one way of looking at it. And the other one, this is what I just mentioned, you sort of protect yourself against shift interventions. And this is another interpretation that I like. This is the regularization with invariance. We tried this out also on real data, so I should really mention this. In the last years, I got more and more interested in looking at real-world data set. I think this is extremely rewarding, and also for me, it helps to understand a bit better or get a better feeling for which assumptions are really necessary to relax. And here I decided to not show you real data with a sort of sad heart, but I wanted to at least try to highlight these connections. This is a method that we tried also on real data, or a variation of this. I talked about this yesterday for kinetic models, but there are, of course, many other applications as well. Okay, I conclude. So causal models predict intervention distributions. This is really the main feature of causal models. And then we talked a bit about causal discovery, that is learning a causal model from data. We spent some time on think about three possible ideas. One is this relation to condition independence, and of course many people here contributed. And the question that maybe algebra could help to get some insight is this relation to continuous random variables that I personally would be interested in understanding a bit better. The second one was this restricting model classes, and there the question is how much nonlinearity is needed. This relates to the question of significance, this intersection of model classes. I think that I have the impression that many of you probably could contribute a lot of good ideas there, because this is really a question about geometry at the intersection. And the last one was exploiting this invariance. Again, there's a lot of structure that can be exploited, and I personally think this is a promising direction to look into. Why? Because you're focusing your model on only one part of the system. You're not trying to model 6,000 variables at the same time. You're trying to model only a small fraction of the model, which I think is appealing. And there are lots of structural constraints in structure we are not exploiting. This is sort of the point is really, so from my point of view, of course, right, I really do think that these questions matter. I mean, it's a question of, there are many interesting things, and I love mathematics, of course, but I also think that it's quite rewarding if you use mathematics for looking at real-world problems, and there are many also natural scientists who have these problems. It's not like that's only advertisement and placement of advertisement that uses data science. There are many natural sciences who are in need for sort of these kind of methods. So this is why I think it's exciting. Last point, if you happen to be interested in these kind of things, this is our book. It's available for free. You can just go to the website and download the PDF and have a look into it. If you are interested in any of these questions, I would be more than happy to talk to you. And with this, I thank you a lot for your attention. Well, thank you.
Thank you, Jonas. Are there any questions?
Thank you for an interesting talk. I'm interested in what one does with the causal model once you've determined causality. So you mentioned that you want to do interventions. Does this help in terms of trying to determine optimal interventions, and if so, how?
Yeah, so indeed there are a couple of things you can do. Personally, I don't think that we should stop at the graph. I think really we should look at interventions, and this has a couple of consequences. Also how you evaluate actually your result. Is it a good graph that you estimated or not? I would say it depends on whether the predicted interventions are accurate or not. And what happens sort of in reality, this is again a personal point of view, I think that we are still in a phase where we are seeing a couple of very promising results on real data, but I would still regard this as a guidance to further follow-up experiments. There's a huge study now in Denmark that we are getting involved in where you're trying to find positive off-target effects from drugs. And this is, of course, like screening, right? Because prediction will not do the trick. So if you just look at prediction, you won't find the interesting variables. So the hope is that these causal methods can actually be a much better filter and say these are the ones that you should look into. But of course, ultimately, I agree. So ultimately, we want to use this for predicting what happens under interventions. Yeah.
Thomas?
Then if you want to do this, what about experimental design? Is there some way of saying which interventions you should try? If you can.
Yeah, there's also some work. I mean, by many people thinking about if you have the option of intervening, what are the most informative interventions? And then most informative means, of course, regarding to what. I personally think that, and of course I blame also myself, we don't know enough from other fields as well. So we are currently looking into also control theory, because they have answers to this as well, right? You already mentioned like optimal design. These are all, of course, questions that are related. And also actually reinforcement learning. You are answering similar questions, right? Because you're intervening all the time and you're trying to find informative interventions. So I would very much like to see more connections there. And maybe I should mention this because I wanted to and I forgot. So I really do think that some of these references I also showed, they help people like me who are a bit outside of this area maybe really to understand things. So they were very nice papers also by Thomas, Seth and others. So I really appreciate this. And of course, it may be a bit boring to write, but I think drawing these connections is extremely helpful. So there's also this, of course, journal of algebraic statistics that many people talked about. I think it sounds interesting to try to sort of close this gap. I think we could at least benefit a lot.
Other questions? Thanks a lot for this comment and for the talk.